7 ancient megaliths that modern engineers still can't fully explain. Not because the tools weren't there, not because the people weren't capable, but because when you run the actual numbers, the weights, the distances, the timelines, the tolerances, the math stops working. Every single time. Let's start with a field in northwestern France, and a stone so large that the people who supposedly built it didn't even have a word for the technology required to move it. Somewhere in Brittany, in a quiet field just outside the village of Lochmariacker, 4 massive fragments of stone lie in a row on the grass. They don't look like much at first, but those 4 pieces were once a single pillar. When it stood upright, it rose to around 20 meters, roughly the height of a 6-story building. Its estimated weight, somewhere between 300 and 330 tons. That is the Grand Menhir Brisé, the Great Broken Menhir, and it is considered the largest single stone ever erected by Neolithic people. Not in France, not in Europe, on the planet. The official version says Neolithic communities built it around 4,700 BC using stone tools, wooden sledges, and coordinated human labor. And that is almost certainly true, which is exactly where the problem starts. The people who moved this stone had no metal tools, no wheel, no pulley systems made of steel. They worked with bone, antler, wood, and harder varieties of rock. The stone itself, the geologists confirmed it is not local. It's orthogneiss, extracted from an outcrop located somewhere between 8 and 10 kilometers away from where it was eventually raised. That means a Neolithic workforce had to drag a 300+ ton mass across uneven terrain, across patches of marsh, across ground that would not have been kind to the kind of sledge system required to move something that heavy. Imagine the numbers. At 330 tons, you're not talking about 100 people on a road. Researchers estimate that keeping a stone of that mass moving over a track of wooden rollers would require somewhere in the range of several hundred to over 1,000 people working in absolute coordination. One mistake in the angle, one roller placed wrong, and the whole operation collapses, sometimes literally, onto the workers below. And moving it was only half the job. Once it arrived, they had to stand it up, 20 meters of stone, completely vertical. To do that, you need a pit, you need a pivot system, you need earthen ramps built at exactly the right angle, and you need to understand the geometry of the load so precisely that the stone tilts upright without snapping or crushing everything underneath it. They succeeded. We know they succeeded because the thing stood for several centuries before someone eventually deliberately pulled it back down. That's the part that doesn't make the headlines. This wasn't a natural collapse. Excavations connected to the Lochmariacker megalithic site research revealed something strange. The menhir was intentionally toppled and broken, and the fragments were repurposed. Parts of it were incorporated into nearby passage graves, the dolmen of Gavrinis, the table des marchands as capstones. The carvings on those capstones, when archaeologists eventually compared them, matched up across the breaks. The pieces fit back together. Same stone, same original monument, deliberately shattered and distributed across the landscape. So the society that spent an almost unimaginable amount of collective energy moving and raising this stone decided, a few generations later, to take it apart. Not randomly, systematically, with enough control over the demolition that they could direct where the fragments landed and then use those fragments as structural elements in other monuments. That's not primitive behavior. That is resource management. That is planned architecture on a generational timescale. And the question it leaves behind, why invest that level of effort into something you're going to dismantle, is one that archaeologists are still working out. But that's not all. Move east. Move about 3,500 years forward in time. Go underground. Beneath the modern streets of Jerusalem, in a tunnel that runs alongside the western wall of the Temple Mount, there is a single block of limestone that has sat in the same position for over 2,000 years. It has survived sieges, it has survived fires. It has survived the Roman destruction of the Second Temple. It has survived earthquakes. It has not moved by so much as a fraction of an inch. This is the Western Stone, and it is, by some measures, one of the heaviest objects ever placed by human hands without powered machinery. The exposed face of the stone measures 13.55 meters in length and 3.3 meters in height. Its depth into the wall was measured by researchers from the University of Wisconsin using ground-penetrating radar in 2006, and the results placed it somewhere between 1.8 and 2.5 meters. Based on those measurements, the weight of the stone is estimated at somewhere between 250 and 570 tons, a wide range that reflects how contested even the basic measurements are. Older estimates, before the radar survey, pushed the number toward 517 to 570 tons. The Western Wall Heritage Foundation currently describes it as weighing several hundred tons. Even at the conservative end, you are looking at a block heavier than any modern crane can lift in a single operation. The stone was placed during the period of Herod's massive expansion of the Temple Mount, somewhere in the late 1st century BC. No mortar, no cement, no adhesive. The Western Stone and its neighbors in the so-called Great Course, a single horizontal layer of enormous blocks designed to act as a structural anchor, were placed using only their own weight and a technique called Herodian drafted margin dressing. Each block was carved with a recessed border around a slightly raised central face, which allowed the edges to sit flush against neighboring stones with joints tight enough that, in some places, you cannot slip a piece of paper between them. The engineering logic is this. By placing extraordinarily heavy blocks at a specific height in the wall, the builders created a concentrated center of gravity that countered the lateral pressure of the earth and fill being compacted behind the structure. The wall was holding back a mountain, and the Western Stone was part of the mechanism that kept the mountain from winning. How did they get it there? The quarry was located a few hundred meters to the north at a higher elevation than the wall. Researchers from the Kotel Heritage Authority suggest the downhill gradient may actually have worked in the builder's favor. The slope allowed the stone to be guided rather than hauled upward, using rollers and ropes to manage the descent. But that descent crossed the Tyropoeon Valley, an uneven terrain of varying elevation, where losing control of a 300+ ton block moving downhill would have been catastrophic. And at the end of the journey, the stone had to be lowered with millimeter-level precision into its position in the course. One theory for how they managed the final placement involves a sandbox technique, resting the stone on a bed of compacted sand and slowly allowing the sand to drain through controlled openings, lowering the block gradually and with a degree of control that a lever system alone could not provide. It's an elegant idea, and it's entirely possible, but no one has confirmed exactly how it was done. What's confirmed is what it survived. 2,000 years of pressure, multiple civilizations building on top of it, Roman soldiers who tried to destroy the wall above it and gave up. The chisel marks from those attempts are still visible on the stone. Here's where it gets uncomfortable. The wall held. The stone didn't move. That's not luck. That is physics applied with a degree of precision that the engineers of Herod's era understood at a level we are still, 2,000 years later, trying to fully reverse engineer. And now we move from a wall built to hold a mountain in place to something even harder to explain. A mountain carved to become a building. In the Aurangabad district of Maharashtra, India, in a range of ancient volcanic hills, there is a temple that exists nowhere else on earth. It was not built from stone. It was not assembled piece by piece. It was revealed. The Rashtrakuta king Krishna I commissioned it in the 8th century CE, somewhere between 756 and 773 AD. And the architects who answered the commission made a decision that still challenges modern engineers. They would start at the top of a basalt cliff and carve downward. Everything that was not a temple would be removed. What remained would be the temple itself, continuous with the mountain it came from, carved from a single unbroken mass of rock. The result is the Kailasa Temple at Ellora, the largest monolithic structure in the world. The numbers are staggering. To isolate the central rock mass, builders first cut 3 deep trenches into the cliff. From that isolated block, they began removing everything that wasn't the finished temple. The courtyards, the central shrine, the surrounding galleries, the colonnaded halls, the elephants at the base, the life-size sculptures, the drainage channels. Estimates of the total rock removed range from 200,000 to 400,000 tons, depending on the source. Historians generally agree the main structure was completed in roughly 18 years. Run that arithmetic. At 200,000 tons over 18 years, you are removing something in the range of 30 tons of dense volcanic basalt every single day. At the higher estimate, it's closer to 60 tons per day. And removing doesn't mean simply hacking it loose, it means breaking it free with iron chisels, hauling the debris out of increasingly deep trenches using baskets and sledges, and doing all of this while simultaneously carving the architectural and sculptural detail of a finished temple. Because the stone removed is gone forever. There is no correcting a structural column once you've cut it too thin. There is no putting back a wall you've chiseled through by accident. The builders had to hold a complete 3-dimensional map of the finished temple in their minds, or on some form of plan we have never found before the first cut was made. One of the most enduring mysteries of the site is where all that rock went. You remove up to 400,000 tons of basalt from a clifftop, and you expect to find rubble. Significant rubble. Archaeologically visible rubble. There are no major debris deposits in the immediate vicinity of the temple that account for that volume. Some researchers suggest the material was used for road building or other construction projects in the region. But the sheer scale of what would need to have been transported makes that explanation feel insufficient. The rock was removed. Where it went remains an open question. And here's the detail that tends to stop modern engineers mid-sentence. The drainage systems built into the temple channels and tanks carved into the living rock to redirect monsoon rainfall still function today, more than 1,000 years after they were first conceived. Now the other side of the world. Same logic, different scale, same question. High on the Bolivian Altiplano, at an elevation of over 3,800 meters, where the air is thin enough to make sustained heavy labor genuinely grueling, there is a site that looks, from a distance, like a field of broken blocks. Up close, it looks like the ruins of something that should not exist. Pumapunku, part of the larger Tiwanaku complex and one of the most precision-engineered stone sites on the planet. The blocks at Pumapunku are not large in the way that the Western stone is large. The heaviest sandstone blocks at the site are estimated at around 130 tons, and the andesite pieces are smaller. What makes Pumapunku anomalous is not weight, it's precision. The H-shaped andesite blocks, some of the most photographed stones in alternative archaeology, show something that researchers describe as sub-millimeter mating tolerances on the surviving joints. A 2018 reconstruction project led by researcher Alexei Vranich, published in the journal Heritage Science, 3D, printed 140 andesite pieces and 17 sandstone slabs from compiled field measurements and physically reassembled them. The joints fit. The modularity was real. These were not randomly shaped stones. They were components of a system designed to interlock in multiple configurations, held together by their own weight and by the precision of the cuts. But it doesn't stop there. The andesite for the facing stones came from quarries near the Copacabana Peninsula, across Lake Titicaca, roughly 90 kilometers away. That transport required moving stones over water and then across treeless, high-altitude terrain where the conventional wooden rollers used at sites like Stonehenge or the pyramids were simply not available in quantity. Llama hair ropes, stone-paved ramps, and sheer coordinated manpower are the leading theories. But for blocks weighing tens of tons, at 3,800 meters of elevation, those theories involve a level of organized labor that required a society far more sophisticated than the term pre-Columbian Andean culture typically conjures in a classroom. Then there are the metal clamps. Cut into the top surfaces of many Pumapunku blocks are I-shaped or T-shaped grooves. Metallurgical analysis of the bronze alloy found in these grooves, a combination of copper, arsenic, and nickel, revealed something unexpected. There is no natural source of nickel in Bolivia. The metal was either imported or smelted from a combination of ores that required knowledge of an unusually specific metallurgical process. And the method of placement. The metal appears to have been poured directly into the grooves in a molten state, on site, meaning the Tiwanaku builders had portable smelting capability operating at 3,800 meters of altitude. The clamps were cast in place. They were not shaped elsewhere and inserted. They were liquid metal poured into carved channels to create a structural bond that also provided seismic resistance, a design feature that makes the blocks function more like a modern earthquake-resistant structure than anything we typically associate with pre-Columbian South America. Coincidence? Possibly. But a series of coincidences that line up this precisely starts to look like something else. Lay the data points side by side. 1. A Neolithic community moved a 330-ton stone between 8 and 10 kilometers over marshland and raised it vertically to 20 meters. Then deliberately and systematically dismantled it and repurposed the fragments, a generational engineering project with no parallel at that date anywhere. 2. Builders working in 1st century BC Jerusalem placed a block weighing somewhere in the range of 300 to 570 tons, the single heaviest object placed by pre-industrial human hands, according to some rankings, using no mortar and no powered machinery, with joints tight enough that the wall survived Roman siege, fire, and 2 millennia of compressive pressure without shifting. 3. An 8th century CE workforce in India removed somewhere between 200,000 and 400,000 tons of basalt from a cliff top in approximately 18 years, carving every column, every drainage channel, and every elephant at the base from a single unbroken piece of the original mountain, with drainage systems that still work today and debris that no one can fully account for. 4. At 3,800 meters above sea level in Bolivia, Builders cut andesite blocks to sub-millimeter tolerances, transported them 90 kilometers across a lake, and cast molten metal alloys into precisely shaped grooves to create structural clamps in alloy that required materials not found anywhere in Bolivia. And that's before you account for the Korean dolmen fields where, across the Bronze Age, decentralized tribal communities moved capstones weighing up to an estimated 200 tons to mark individual burial sites, thousands of them, requiring organized inter-community cooperation on a scale that, by the logic of the era, shouldn't have been possible. Or the Japanese Kofun mounds, where engineers maintained perfect keyhole-shaped geometry over distances of 500 meters a shape, only visible from the air, and encircled them with moat systems engineered to maintain constant water levels through seasonal monsoon flooding. Or the Al Nisla rock in northwestern Saudi Arabia, a sandstone monolith split so cleanly down a vertical line, with both halves so perfectly aligned, that the grain patterns and the ancient petroglyphs on the surface would match up if you press the two halves back together, a split that geologists attribute to frost weathering and erosion, but that left no displacement, no shattering, and no fragment out of place. 7 sites. 7 problems that the official explanation handles partially, but not completely. The official version is not lying to you. The textbooks aren't suppressing anything. The researchers who study these sites are asking the same questions. But there's a difference between we have a plausible theory and we can fully explain how it was done. For every site on this list, the honest answer from the field is, we have partial explanations. The full picture isn't there yet. And that gap, that space between what we can measure and what we can explain, is where the interesting questions live. We think of ancient engineering as primitive because the tools were simple. But the data keeps suggesting something different. Not aliens. Not lost technology in some science fiction sense. Something more unsettling. The possibility that the organizational and cognitive capacity required to solve these problems was present in human societies far earlier, and at far greater scale, than the standard timeline of civilization comfortably allows. The stones were moved, the walls were built, the temples were carved. The math mostly doesn't work with the tools and the timelines we've assigned. That's not a theory. That's what the measurements say. What stands above the ground is only half the story. Next, we go beneath it underground complexes carved thousands of years ago that no one has fully mapped in places the textbooks don't mention. The evidence is stranger than you think, and it's been sitting there waiting to be found.